In this lecture, we will reread machine translation through the nDNA lens. Earlier, we described each language with a neural genome made of 3 coordinates: spectral curvature, which tells us how the latent space bends; thermodynamic length, which tells us how much epistemic work the model performs; and the belief vector field, which tells us where its internal beliefs spin. Now we treat translation as aligning to such genomes, and we measure how hard that alignment is without generating a single word. This is the idea behind GENOME-MT, a generation-free, zero-shot evaluator that explains transfer difficulty using two signals: semantic torsion, which is the amount of twist between the two semantic spaces, and epistemic force, which is the latent effort required to move between them. We combine them into a single total epistemic effort score that tracks standard MT metrics such as BLEU, COMET, and CHRF. You will see that closely related pairs like English to French, German, or Italian show low torsion and short paths, so the effort is small and quality is higher. Typologically distant pairs like English to Chinese, Thai, or Japanese require long, twisted routes, so the effort is large and quality is lower. With this view, we can budget difficulty before deployment and place the right fixes, add small homology adapters to shrink distance, use reordering curricula to ease torsion, and apply geometry-preserving distillation to keep curvature healthy during compression. By doing so, machine translation stops being a black box and becomes a readable set of genomic edits in latent space, with diagnostics you can act on. Now let us dig deeper to understand the idea and mathematical construct of the epistemic effort for machine translation within models' internal geometry. We do not score translation quality by generating text. Instead, we read the two languages inside the model and measure how hard it is to move meaning from one to the other. That hardness has two parts. The first part is semantic displacement, how far the latent representation for English sits from the latent representation for the target language at each layer or reverse. The second part is semantic torsion, how much the local trajectory of meaning twists when you try to go from one language to the other. Displacement captures how far, torsion captures how crooked. For each transformer layer, we measure two things. Per layer L, we compute two terms. Semantic displacement, how far the English and target language representations are from one another for the same content. Let d sub L be the length of the difference between the target vector at layer L and the English vector at layer L. Semantic torsion, how their directions of progress differ across depth. Compare the layer-to-layer change in English with the layer-to-layer change in the target. When these directions align, torsion is low. When they twist or cross, torsion is high. Let d sub L be 1 minus the cosine of the angle between tangent 1 and tangent 2. When these tangents point in the same direction, t sub L is small. When they twist or cross, t sub L is large. To have the total epistemic effort, we then sum across layers a displacement term multiplied by a torsion amplifier. This produces a single score, total epistemic effort, that is low for smooth, well-aligned transfers and high when the model must both bridge a large gap and untwist misaligned paths. Let omega sub L be a layer weight. Define E total as the sum over layers of omega sub L times d sub L times 1 plus t sub L. In practice, total epistemic effort score tracks metric in quality, BLEU, COMET, CHRF without generating translations, and it naturally supports directionality. English to X and X to English can have different effort because their depth-wise progress vectors can differ. Why this works? Displacement alone often misses structure. Two languages can be close in space but require a twist to swap subject-verb order or to unpack an idiom. Torsion adds that structural tax. When displacement is small and torsion is small, the model can transfer meaning with little effort. When either is large, especially both, the model must do more cognitive geometric work and zero-shot quality drops. In short, total epistemic effort is a generation-free, geometry-first predictor of translation difficulty. Distance tells how far the concepts must travel. Torsion tells how much untwisting is required. The layer-ways sum is the energy bill for moving meaning from one language's semantic genome to the other. Machine translation quality is inversely proportional to epistemic torsion. As the latent path between two languages twists more across layers, the model must spend extra mental fuel to reorient and quality drops. Torsion captures this twisting of depth-wise progress. When English and the target language move through the network in aligned directions, torsion is low and transfer is smooth. When their directions diverge or cross, torsion is high and errors grow. Displacement still matters. The farther the two meanings sit apart, the more work is needed, but torsion is the amplifier that turns a gap into real difficulty. Put simply, short, straight routes predict strong zero-shot MT, Long, kinked routes predict weak MT. We see three major patterns. Latin script families such as English with French, German, or Italian show the smallest effort and the best predicted quality. Word order and morphology are closer, so the manifold bends gently and paths stay aligned. Indian language pairs such as English with Hindi, Bengali, or Tamil sit in the middle. Scripts differ, agreement and case cues change, and reordering is more frequent. Displacement grows and torsion spikes in mid-layers, so effort and predicted difficulty rise. East Asian pairs such as English with Chinese, Japanese, or Thai show the largest effort and the weakest predicted quality. Segmentation, syntax, and discourse packaging differ substantially. The path becomes long and kinked, torsion is high, the model must repeatedly untwist its route across depth. We also witness directionality in empirical results. Effort from English to language X can differ from effort from language X to English. The progress vectors through depth are not symmetric, so one direction can be smoother than the other. The metric captures this automatically. Why this is useful operationally? Because we never decode a sentence, we can screen many language pairs quickly, triage high-risk directions, and choose better pivots or adapters before deployment. Low effort suggests robust transfer and stable quality. High effort flags where we should add supervision, plug in small adapters, or adjust the alignment schedule. Now, let's see epistemic torsion and directionality in action for all the three language families. English to Latin script languages, French, German, Italian, show the easiest transfer in our nDNA view. The English and target trajectories run nearly parallel across depth, torsion stays low, and the forward and backward epistemic forces are small and balanced, so total epistemic effort is minimal. French is the smoothest path, with the most uniform curvature. German shows a small mid-stack bump from verb movement and case marking. Italian has a late layer kink from morphology, yet all three remain modest. Result: high blue in both directions, roughly in the high 30s to low 40s. Why? These languages share SVO word order, similar analytic structure, and substantial lexical overlap with English, so little reordering is required and the model can walk a short, straight route in latent space. Conversion between English and Indian languages such as Hindi, Bengali, and Tamil show a clear step up in difficulty in our nDNA view. Paths are longer and twistier than the Latin set, and the forward and backward epistemic forces are bigger and less balanced. Total epistemic effort sits in the middle tier. Why it happens? These languages are verb final and rich in morphology. Moving from English subject-verb-object order to subject-object-verb requires deep reordering, plus handling compound verbs, postpositions, and case marking. In the plots, you can see a large forward push in the mid-stack as the model reorganizes clause structure, followed by a backward correction near the top where morphology and agreement get resolved. Hindi shows a pronounced mid-layer push and a late correction. Bengali follows the same pattern with slightly higher mid-layer effort. Tamil is the most torsional of the three, with strong late-layer adjustment driven by agglutinative endings. Outcome: blue lands in the mid-20s. Directionality also shows up. English to Indic is usually harder than Indic to English because creating verb final order and packing morphology costs more epistemic work than unpacking it. English paired with Asian languages, Chinese, Thai, Japanese, are the hard end of the spectrum. In the nDNA view, these pairs show the longest paths and the highest torsion. Mid to late layers spend a lot of forward epistemic force to rebuild structure, then fire large backward corrections, evidence that the model must both bridge a big gap and untwist misaligned routes. Why so hard? Chinese relies on classifiers and is largely topic prominent with little case marking. Thai is analytic with serial verbs and flexible word order. Japanese is head final and agglutinative with heavy scrambling. Those properties force deep clause reassembly rather than surface edits, so curvature stays high and length keeps growing. What the plots show. Chinese, a strong forward push around the mid-late stack followed by a tall backward spike, persistent misalignment. Thai, a long high effort run with a late correction, structure is rebuilt late. Japanese, the strongest forces near layers 26 to 28 and the most twisted path, maximal reordering load. Outcome. Blue sits in the low teens to about 20, and directionality is pronounced. English to Asian languages costs more epistemic work than the reverse because it must create topic or head final order and insert classifiers, not merely unpack them. GENOME-MT, summary of our experiments at a glance. Total epistemic effort score predicts MT quality. It is epistemic distance times a torsion amplifier, summed across layers, tracks zero-shot blue and comet without decoding. Across all pairs, we observe a strong inverse relationship. When effort is low, blue is high, and vice versa. Pearson correlations are about 0.9 in both directions. Spearman ranks are about 0.9 as well. Direction matters. English to X and X to English often have different effort, reflecting asymmetric depth-wise progress. GENOME-MT captures this asymmetry directly. Latin script pairs are easy. English with French, German, and Italian show the lowest effort and the highest blue, around 39 to 43. Linguistic reasons, SVO order, analytic structure, modest case marking, and limited reordering, torsion stays small. Indian languages are mid-difficulty. English with Hindi, Bengali, and Tamil land in the mid-range effort with blue in the mid-20s. Causes, SOV order, compound verbs, agglutinative morphology, and script and morphosyntax divergence, torsion rises in mid and late layers. East Asian pairs are hardest. English with Chinese, Thai, and Japanese show the highest effort and blue in the low teens to about 20. Drivers, classifier systems, tone and aspect, topic prominence, scrambling, head final structure, and the lack of case markers, torsion is consistently high and long corrections appear late. In summary, let us understand what distance and torsion explain. Distance reflects how far the two semantic motifs are at each layer. Torsion reflects how much the layer-to-layer directions disagree, i.e., how much topological untwisting the model must do. Low distance plus low torsion means cheap, robust transfer. High distance plus high torsion means costly, brittle transfer. Final takeaway. Epistemic effort score is generation-free, language agnostic, and fast. It provides a pre-deployment estimator to flag hard directions, plan data or adapter budgets, and choose safer routes for multilingual transfer before any translation is produced. Total epistemic effort is analogous to genomic homologous recombination. It is the cell's high-fidelity way to fix double-strand DNA breaks, in other words, a measured cost of making a precise, structure-preserving match between two closely related sequences. When a chromosome breaks, damaged sensors recruit the repair machinery. The broken ends are cleaned, and a search is launched for the matching sequence on the intact sister chromatid. The broken strand then invades its twin, copies the missing information, and the temporary crosslinks are resolved so the original code is restored and genomic integrity is preserved. By analogy, total epistemic effort measures how hard a model must work to make an equally precise splice of meaning between two languages. Distance captures how far the latent representations must slide to line up. Torsion captures how much untwisting is required when their internal progress differs, and the sum across depth is the overall repair bill for a clean, faithful transfer of meaning. For a quick understanding how genomic homologous recombination works, let's have a glimpse over this clip. Here's the conclusive biological analogy that ties it all together. Machine translation behaves like homologous recombination. Each language is a genome of meaning. When two genomes are syntenic, similar order and structure, the system finds matching loci quickly, copies the missing pieces, and finishes the splice with little strain. When the genomes carry inversions or translocations, the strands must be untwisted and realigned before copying. That extra untwisting and rerouting is exactly what our torsion and distance terms capture. Attention plays the role of the homology search. The clean splice itself is measured by total epistemic effort, the work needed to align, untwist, and carry meaning across depth. Here's the story behind the math on this slide, in plain language. For each transformer layer, we collect mean-centered hidden states for the source language and the target language. We then solve a simple orthogonal procrusts problem, find the best rotation that aligns the source cloud to the target cloud at that layer. The residual after this best rotation is the homology gap, a layer-wise distance that says, even after optimal alignment, how far apart are the two languages here. You can read the same quantity through principal angles between the two subspaces. Both views give a clean, comparable distance per layer. Next, we track a belief direction in each language, a normalized steering or task gradient, and measure their torsion, which is the angular misalignment of those directions once you transport them into a shared frame. Intuitively, distance tells you how much sliding is needed to match loci. Torsion tells you how much untwisting is required to make the match stick. We also read a curvature profile from how the aligned bases rotate as depth advances, and we accumulate a thermodynamic length that summarizes the total epistemic step the model takes through that layer. Summing these pieces across depth, with torsion acting as an amplifier on the length, yields the total epistemic effort, a single score that is low for smooth, well-aligned language pairs and high when the model must both bridge a gap and untwist misaligned paths. We define one difficulty score, E total. It is the layer-wise sum of three terms, the homology gap d sub L, which is the residual distance after optimal rotation, an untwisting cost tau sub L, which measures misalignment of belief directions, and a curvature penalty kappa sub L, which captures how much the aligned basis bends with depth. You may weight each layer by its thermodynamic length L sub L to emphasize regions where the model does the most work. Low E total means a smooth splice of meanings. High E total means the model must both bridge a gap and untangle paths. Let's understand biology to ML mapping. When the two semantic chromosomes are syntenic, meaning word order and constructions are stable, both D sub L and tau sub L stay low. Structural variants such as inversions, translocations, duplications, and deletions appear as order flips, topic comment structures, classifier systems, or null elements, and both distance and untwisting costs rise. Strand exchange corresponds to attention creating locus matches. Topoisomerase-like action is the depth-wise untwisting captured by tau sub L. Mismatch repair is pruning implausible alignments using belief consistency. Micromechanics visible in the curves. Ambiguity behaves like a holiday junction. Competing alignments create a junction in latent space that resolves as a sharp drop in D sub L with spikes in kappa sub L or tau sub L. Gene conversion, also called directional overwrite, occurs when dominant prios overwrite rare target forms, producing asymmetric difficulty for English to X versus X to English, which appears as drifting belief directions and elevated tau sub L. Polymerase slippage, or repetitions, looks like local loops around high-gain engrams. D sub L remains small while kappa sub L oscillates upward. Final takeaway. E total is a generation-free, layer-wise bill for translation. Minimize distance to tighten homology, minimize torsion to ease untwisting, and smooth curvature to avoid jagged detours. Use this score to predict machine translation quality, localize failure, and choose the right intervention, adapters to shrink d sub L, reordering curricula to shrink tau sub L, and geometry-preserving compression to tame kappa sub L. Please refer to the book for further details and derivations.